All right. So what I did is I popped in, ideally correctly, the two matrices, but they're defined as the inverse of A and inverse of B. But the calculator, I can't just say let this be. It's not going to say matrix A inverse. It'll just say matrix A. I just have to know that it's the inverse. So in doing so, I can manipulate things. Now, instead of racking my brain to think about all the different possible ways to algebraically or otherwise uh, know these relationships, what I can do is actually find the inverse. Now, it also might be against the school's policy to for something like that. That's a different story. You know,
But it's allowed in most cases.
correct. All right, so now these are labeled as the inverse, but this is really just matrix A, and this is matrix B. All right, so what I'm going to do is I'm going to store those in as C. And D. All right, so everywhere that I see an A, it's really a C, and everywhere I see a B, it's really a D. So now I can just burn through these calculations. And again, there's properties that you can rely on, but this is a I don't have to think about stuff approach.
Why did you use A for the third one and D for the?
Oh, it should be C. Because I saw an A and I just wrote it. And
I have a question.
sure.
This is kind of off topic.
Okay.
What is there like a Taylor series for a cross multiplication
Taylor series for cross multiplication of.
of like matrix?
It depends on what you're cross multiplying. If you're, let me just do this. Because if you're doing, let's say, a derivative or antiderivative transformation matrix, and it has some sort of transcendental in it, like a e to the x or a sine function, cosine function, then you can put it into a Taylor and make it a Taylor polynomial, and then create a a transformation matrix based off of that polynomial to some high value of n. But that's just one example. But I'm sure there are other possibilities.
So with a problem like this, if you're given the inverse generally, should you expect to like convert it to the normal before you do any?
Yeah, that's unless you're actually relying on on properties, because a b to the inverse of a, the product of a and b is the product of the inverses of a and b. So you can, if you know that, you can go to it. You know.
Yeah, you can do either or.
Right.
In that scenario.
The one concern about this approach is that that's trying to tell you zero. That's calculator lingo, and that's par for the course. Okay, so for this guy, what we're looking for is a case of, well, obviously where the inverse exists, and if so, what is the inverse? Um, and you know, if we come up with the A value, then we can kick over to the calculator. But what we need to do is determine situations in which the determinant is not equal to zero. All right, so you could do it. I mean, for this one, because the numbers are kind of nice, if you wanted to use the replication shortcut, you know, where you take the columns inside and reproduce the first two columns and reproduce them outside, you could. But also, I mean, I think it's going to be okay with cofactor expansion because you have a nice row to work with here. Yeah, it's got a bunch of zeros in it. So if you were to say I have one that has the position of row 2, column 1, and if we eliminate the row and column that contains the 1, so we'd have 1, 0, 2, A. And then, you know, you go down the line, you'd say 0, and then negative 1 to whatever power, and then the determinant of whatever 2 by 2, and then a 0 again, but those are going to zero out. So this is the only one I'm actually concerned with. We'll actually set this equal to 0 to find out the entries of A that would make a singular matrix. We're looking at negative 1, diagonal down is A, minus diagonal up, which is 0. So negative A equals 0, so A equals 0. So A equals 0 is the only bad value. Yeah. Now the part where we actually find the inverse, a little bit of a different story. Because we end up with a situation, because this will make, if A is equal to 0, then it makes the determinant equal to 0, and that's the only bad situation. In order for the inverse to exist, A can be literally anything other than 0. So in order to find the inverse, I have to allow for any possible value of A other than 0, which is going to require me to sit down. So I'll call that part A. Part B, the numbers are nice, relatively nice, so it might not be that bad. So it'll work in terms of A. So we need to get down to reduced row echelon form. So the first step, I think, would be to swap row 2 with row 1. That's another 1 for some reason. All right. I'm good, obviously, in row 1. In row 2, I can get rid of the first entry here by doing a negative R1 plus R2. All right, so then I have a few things that need to go away. So I can do a negative. Actually, let me erase the bottom row because it could have been a simultaneous step. Negative R1 plus R3 would have been 0 to A 0 negative 1 1. Then negative 2 R2 plus R3. So 0 0 A negative 2 1 1. And then the last step would be just to multiply row 3 by 1 over A. So the inverse of A would be that. And that does at least coincide with what we determined A couldn't be, because if A is equal to 0, then this bad boy is undefined. So at least it's consistent. Not the linear algebra word consistent, but normal people speak consistent.